Hello everyone, this is Dr. Fan. One of my students showed me this question and I want to share it with you. This question is pretty interesting, but at the same time, it's very tricky. Even his teacher got it wrong. Let's discuss it today. In this question, there are three blocks, small m, big M, and full M. In the beginning, all the blocks are at rest, and the pulley string are massless and frictionless. So the question asks, after the system is being released, which block can remain at rest? And for what ratio of small m over big M is it possible? My student teacher said, alright, I got full M and I'm on this side. So in total, I got 5 mg. And on the right side, I got mg, small mg. So as long as I make small m equals to 5 times big M, then my system should be at equilibrium. So my small m could be at rest. This is the reasoning from the teacher. But this solution is wrong. The main reason is the lower block right here is movable, but also full M is heavier than M. So this string has a tendency to go down and this string has a tendency to go up. So let's discuss the correct solution for this question. Alright, so if we look at this question, we can choose going up as my positive direction. Then I know on small m, I have tension. Let me call it T1. And on M, I also have a tension. I call it T2. And on full M, I also have tension. I call it T2. The reason these two tensions are the same because they are along the same string. Alright, now I can draw the free body diagram on small m, which is mg going down and T1 going up. Very straightforward. And for M right here, I got the same thing. Big mg going down, T2 going up. For full M, it's the same thing. I got gravity going down, full mg, and I got tension T2 going up. So now I can write down Newton's second law for all three blocks. So for small m, this is what I got. I got sigma F net equals to T1 minus small mg equals to small m times the acceleration of small m. I call this equation 1. And for m, my net force equals to T2 minus big mg equals to big M times the acceleration of big M. I call this equation 2. And for the full M block, my net force is T2 minus full mg equals to full M times the acceleration of the full M blocks. I call this equation 3. So if I look at all these three equations, I saw T1 and T2. I got two unknowns, but I also saw AM, the acceleration of small m, and the acceleration of big M, and the acceleration of full M. So I have 5 unknowns. In order to solve this question, I need more equation. In other words, I need more relationship between the variables. If I pay attention to this movable pulley, I notice something. Because for this movable pulley, I got tension T1 pulls it up, and I got tension T2 on both sides pulling it down. So for the movable pulley, I can write down its net external force. So the net external force equals to T1 minus 2 times T2 equals to the mass of the pulley times the acceleration of the pulley. And I call this equation 4. But I know the pulley is massless, so T1 minus T2 basically equals to 0. So I got my fourth equation. Then I need one more equation. The last equation comes from the fact the strings are not stretchable. So how will this help my calculation? Because the strings are not stretchable, so the acceleration of small m, am going up should be the same as the acceleration of pulley AP going down. They have the same magnitude but opposite direction. In other words, AP, the pulley's acceleration, this movable pulley, should equal to minus am, the acceleration of this small m. Now let's look at this second string here. If we use this movable pulley as my reference, the acceleration of m going up should equal to the acceleration of 4m going down. That means the relative acceleration of m relative to pulley equals to the relative acceleration of 4m relative to pulley, but they have opposite direction. And I know the acceleration of pulley is am, and I know pulley has an acceleration of minus am. So this acceleration should equal to am minus ap. And I can do the same for the relative acceleration of 4m, which equals to minus a 4m minus ap. If I substitute AP as minus am, what I got is my last equation, which is am plus a 4m equals to minus 2 times a small m. And that's my fifth equation. I have 5 unknowns, t1, t2, and I have 3 accelerations, a small m, a big M, and a 4m. So if I combine all these equations and solve all of them, this is what I get. For small m, my acceleration is, it equals to 16m minus 5 small m divided by 16m plus 5 small m times g. For m, its acceleration is 11 small m minus 16m divided by 16m plus 5 small m times g. And for 4m, its acceleration is minus 16m plus small m divided by 16m plus 5 times small m times g. If I want my block to be at rest, I just need to make sure the acceleration equals to 0. Therefore, if I want the small m to be at rest, I just let am equals to 0. In that case, 16m equals to 5 times small m. And if I want m to be at rest, I just let am equals to 0. And in this case, 11 small m equals to 16m. And if I want the 4m to be at rest, I just let a 4m equals to 0. In this case, I got 16m equals to minus small m. As you can see, I can let small m to be at rest, and I can let big M to be at rest, but I cannot let 4m to be at rest. Why? Because look at this relationship. One of the mass has to be negative, but we know mass cannot be negative. That means 4m can never be at rest, and my small m and big M can be at rest. And this is the ratio if you want small m to be at rest, and this is the ratio if you want big M to be at rest. I hope you guys like this question. I will see you next time. Thank you.